Welcome to your presentation on arterial blood gases, or ABGs. Most of this should be a review, but it's just to ensure that you have a solid foundation before we build on these concepts in class. You can see the learning objectives here. We'll be talking about some of the basic patho behind ABGs and then get into the components of ABGs, how do you interpret those, but then most importantly, once we know what the arterial blood gas disturbance is, what could have been the cause, and then what can we do for that patient. So let's take a step back for a second. Why are we looking at ABGs? Why is acid-base balance important in the body? Well, first of all, it's important to look back to homeostasis. So we need to have this balance in the body, and specifically the pH of our blood, to sustain life. So it's important to recognize that not only is the pH of the blood important, but also to recognize what could have caused that change in the pH. And then remember that an acid-base imbalance, so for example, metabolic acidosis, is not a disease in itself. It's actually the result of another process going on. So different disease processes and conditions can lead to acid-base disturbances. So you can see some examples here, but this is kind of the crux of ABGs, where we can look at what the disturbance is, but less important what the disturbance is than what caused it, and there could be a number of different conditions that could cause the same arterial blood gas disturbance. So let's start off more literally. How do we get an ABG? Well, as the name states, this is arterial blood. So we can't get an ABG from regular lab draws that are venous. It must be drawn from the artery, either as a peripheral stick with a needle or through an arterial line. Now, because ABGs can be very challenging to draw and can also be really, really painful for our patients, it's important to think about who might need to get frequent ABGs and how we can make this more manageable. So for example, if a patient's on a mechanical ventilator and we're essentially breathing for our patients, and we want to see if changes in how we're breathing for them and how that might affect our patient, if those are working, we're going to need to draw a lot of ABGs. And in that case, it might be best to have an arterial line so we're not constantly poking our patient to get these lab draws. Now, one more thing to think about with ABGs. Why do we even need arterial blood? Why do we even want to look at this arterial blood and these arterial blood gases? What makes it so special? And why is it worth all this work and potential pain and risk to our patient? Well, think about what that blood is doing and where it has just been. It's just left the heart. So it's just been oxygenated, we hope. Our venous blood is actually just dumping off oxygen. So when we check our venous labs, it's going to be very oxygen poor. So arterial blood can tell us about how well that patient just oxygenated blood in their lungs. And this is the most unique thing about it. Just keep in mind that arterial blood has a lot of other really helpful information as well. So one last thing to remember, ABGs are an assessment tool. They tell us about a lot of things, one of which is oxygenation. So let's say we just suctioned our patient in the ICU, or maybe we made a change to the mechanical ventilator, and we want to know, how is my patient doing now that I did that thing for them? Well, in order to assess the effects of that change on our patient's oxygenation, we can't just immediately draw an ABG and see our answer. The effects of our actions haven't really kicked in yet. We need to wait at least 20 minutes after we did that thing to help our patient, and then draw an ABG to see the effects of it. So in a sense, we need to wait for the dust to settle to determine what really happened to our patient's arterial blood gases as a result of what we did for our patient. So we've drawn an ABG. Maybe it was a peripheral needle stick, usually done by the respiratory therapist in the state of Arizona at least, and we get these results. We get this blood and we get the results. And sometimes they'll be printed out like you can see here on a little piece of paper. Eventually they're going to show up in our patient's chart, and now we need to make sense of these numbers. So here we'll discuss the specific values that are found in the arterial blood gas results. Again, a quick disclaimer, this is not all-inclusive and is actually quite simplified, but we're really focusing on the information required to read and interpret an acid-base disturbance. So we will need to look for some important values: the PaO2, the SaO2, the PaCO2, the HCO3, and the pH. Note that we have two oxygen values here, the PaO2 and the SaO2. Now you can think of the PaO2 as the more broad value and the SaO2 as more specific. So what do I mean by that? Well, the PaO2 is the total amount of oxygen in the bloodstream. It's the partial pressure created by all the oxygen molecules in the bloodstream. We don't know much else about these oxygen molecules, but we know that they're there. Now, because PaO2 is a partial pressure, it's actually measured in millimeters mercury, just like your blood pressure. And a normal PaO2 is 80 to 100 millimeters mercury. Just keep in mind, you can have too much oxygen, and the PaO2 can go over 100. Now, don't get this confused with SaO2, which is measured in percentages. Note that SaO2 is actually looking at the hemoglobin, and we're really asking, what percentage of all of these hemoglobin floating around in the bloodstream, what percentage of them are saturated with oxygen? Now, we'd like most of them to be saturated because that's their job. They're supposed to carry oxygen. So that's why we often look for an SaO2 of over 95%. And sometimes this varies depending on our patient's comorbidities, though, just FYI. So next, we're looking at the total amounts of two important compounds, CO2 or carbon dioxide and HCO3 or bicarbonate. Now, the amount of CO2 in the arterial blood basically tells us how much CO2 did we just get rid of in the lungs by exhaling, or how much was left behind by maybe not exhaling so effectively. So a higher level of CO2 in the arterial blood tells me that I didn't really get rid of very much CO2, maybe when I was exhaling or due to another issue, but I didn't blow off a lot of CO2, so now it's stuck around in the bloodstream. And then really low levels of CO2 tell me that I did a really good job, maybe too good of a job, getting rid of CO2, and I must have been exhaling really, really deeply and quickly. Now, bicarbonate, or HCO3, really tells us about the metabolic system, and it's controlled by the kidneys. So if my kidneys are retaining bicarbonate and not urinating it out, then I'm going to have higher levels of bicarbonate floating around in my blood. If my kidneys excreted more bicarbonate in the urine, then there's going to be lower levels of bicarbonate left in the bloodstream. Now, last here is the pH. As you recall from your chemistry classes, pH is the scale from 0 to 14, representing the acidity or alkalinity of a substance. So remember, this is related to hydrogen ions. The more hydrogen ions there are, the more acidic something is. And the less hydrogen ions that are present, the more alkaline it is. And you'll recall that a lower pH is acidic and a higher pH is alkaline. So let's look at pH a little bit more. When we look at pH in the blood, you might expect it to be a perfect neutral pH of 7, smack dab in the middle of 0 to 14. However, notice here that a normal arterial blood pH is 7.35 to 7.45. So when our patient has a pH below 7.35, we call that acidosis or acidemia. And if their pH is above 7.45, we then call that alkalosis or alkalemia. So why is our blood just a little bit alkaline? Well, you can see a little scale here where in our blood, we keep a whole lot more base bicarbonate than carbonic acid. But more carbonic acid may be due to a disease process or another problem that could tip the scale so that our patient becomes more acidic, and vice versa, increasing this ratio of 20 bicarbonate to 1 carbonic acid to a greater gap that could have too much bicarbonate. That will send our patient into alkalosis. So looking at this, looking at our arterial blood pH, now our truly smack dab in the middle normal pH point for blood is 7.4 actually. Normal is 7.35 to 7.45, but the true smack dab in the middle is 7.4. So which is worse, acidosis or alkalosis? Well, you can see here, one is not necessarily more dangerous than the other. It's really more about how extreme the acidosis is or how extreme the alkalosis is. So a very acidic pH at like 7.0 or getting close to 7 or 6.8, that is likely fatal. Just like a very alkaline pH getting close to 7.7 or 7.8, that is also likely fatal. So remember that your blood pH and my blood pH and your patient's blood pH can all be affected by a lot of different things. Think about how lactic acid builds up when you go to the gym. That can lower your pH because there's now more acid in your bloodstream. Or when you take antacids, those are medications that are basic and they can raise your pH. So how do our bodies normally handle these fluctuations? Well, we have a few systems in place to be aware of. These are regulatory or compensatory mechanisms to bring that pH back into normal range of 7.35 to 7.45. So what are they? Well, first is our buffer system. These are proteins, ions, and other substances that immediately respond to changes in the pH within seconds. The buffer system is the quickest system to respond to a pH change and can neutralize weak acids or can weaken strong acids. And that sounds great. However, one thing, the buffer system has a low threshold. It's not going to be able to handle big changes in pH, and it kind of tires out quickly in a sense. So if that system kind of tires out in a sense, then what other systems do we have in place to bring our pH back to normal if it's too high or too low? Well, our respiratory system can jump into action next. Now remember, the buffer system kicked in and went to work immediately within seconds, but our respiratory system takes a few minutes and then it can get to work to try to correct a pH and bring it back into normal range. We'll get into the details of how it does this soon, but essentially by changing the breathing pattern, depth, and breathing frequency. By doing that, our lungs can try to normalize a pH. But we can't change our breathing pattern forever. So even our respiratory system doesn't regulate the pH indefinitely. It usually can only compensate for up to a day, but not long term. So what system can try to correct a pH longer term? Well, that is our renal system. Our kidneys can step in and make changes to hydrogen ions. Remember, hydrogen ions directly relate to pH. Or our kidneys can make changes to bicarbonate, which you'll remember is a base. Now, the kidneys can make these changes for a much longer term than both the buffer system and the respiratory system. And the kidneys' changes to the pH are much more sustainable solutions. Just note that it can take a little while for those kidneys to kick in and start trying to correct the pH. The kidneys might take hours or even days to start to work on the pH problem. So taking a closer look at the buffer system, you can think of these little buffers kind of like sponges in a sense. They soak up hydrogen ions when there's too many in the bloodstream and the blood is too acidic, and they can release those hydrogen ions into the bloodstream when there's not enough hydrogen ions or when the blood is too alkaline. So as mentioned before, the buffer system has the capacity to weaken strong acids or neutralize those weaker acids. So remember, this is the fastest system to attempt to regulate an abnormal pH. However, the buffer system can't act alone, and it needs to work with the respiratory and renal system to truly regulate pH. So if our buffer system can't do all the work alone, how do our kidneys and lungs regulate pH? Well, put simply, the respiratory system can increase and decrease the level of CO2 or carbon dioxide, and the renal system can increase and decrease levels of hydrogen ion and bicarbonate. Now, we'll go into how they do that soon, but why should we care about CO2, bicarbonate, and hydrogen ion, and how do they affect pH? Well, let's look at the compound H2CO3. This is carbonic acid. So, if we were to break apart this compound, let's say we just break off one hydrogen ion. We now have that one hydrogen ion and bicarbonate left over. And that is something that the kidneys can work with. The kidneys can get rid of hydrogen ion now, or it can get rid of bicarbonate in the urine, or it can retain either one of those in the blood. So depending on whether or not we need more or less base or more or less acid in the blood. Now we can also break H2CO3, that carbonic acid, into water and carbon dioxide. If we take both hydrogen ions and one oxygen atom, that's water, H2O, then there is still one carbon atom and an oxygen molecule left over. So we have water and carbon dioxide. So if we wanted to get rid of acids, we could blow off one of those building blocks, CO2, and the more CO2 we blow off, the less there is available now in the blood to make carbonic acid with water that's readily available in our bodies. So conversely, if we breathe really, really slowly or ineffectively, there's more CO2 staying behind, not getting blown off and now remaining in the bloodstream. So that can readily combine with water and now create carbonic acid. So to oversimplify, you can think CO2 equals acid. More CO2 in the body will lead to more acid. Less CO2 in the blood means more basic. So let's look at the respiratory system a little more closely. Now remember, the lungs can kick in within minutes and are actually twice as effective as the buffer system, but its effects can only last up to a day. Now, as I mentioned before, when we exhale, we blow off CO2. Remember, CO2 travels in the blood from our venous system to our lungs, into our alveoli, and we exhale and get that CO2 out of the body. If we exhale a lot, if we breathe deep and fast, we will get rid of a lot of CO2, and therefore we essentially took a lot of CO2 out of the bloodstream. Now, if we're breathing really ineffectively, maybe our respiratory rate is 8, and we're breathing really shallowly, the CO2 can't get out as easily, so it just stays around in the bloodstream. So think of it this way. Deep and very effective, or even hyper effective breathing gets rid of a lot of CO2. So less CO2 sticking around in the bloodstream means less building blocks for acid, and we get more basic, and our pH should go up. Now, if we breathe more slowly and ineffectively, we're not getting rid of CO2 as well, so it stays in the bloodstream, and then we have more building blocks for carbonic acid. Now, a normal carbon dioxide level in the arterial blood is 35 to 45 millimeters mercury. If we have a pH problem that's due to a metabolic problem, let's say we're in diabetic ketoacidosis, something outside the lungs is causing the pH to drop, and we call it metabolic acidosis. So our lungs will kick in and compensate. They'll say, looks like you have a too much acid problem, and I can help with that. As the lungs, I'll get rid of some of those acidic building blocks, carbon dioxide, and I'll breathe deep and fast. Now, on the other hand, let's say you took way too many antacids and your pH is really, really high. It's very alkaline. And the cause is, again, a problem besides your lungs. It's outside the lungs, so we would call it metabolic alkalosis. Now our lungs look at that and say, you have an alkaline problem. To fix this, you need more acids, and I can help with that. So I'll give you more building blocks to make carbonic acid. And we start to breathe really slow and more shallowly. And we don't blow off and we don't get rid of CO2 as much, those building blocks. So it stays in the bloodstream, and we now have more building blocks to make more acids, which helps us compensate for that metabolic alkalosis. So now looking at our slowest but most sustainable compensatory mechanism, and that's the kidneys. Now remember, our renal system can take hours and sometimes a day or so to kick in, but this is also the most sustainable solution to a pH problem. So how do our kidneys do it? Well, remember that carbonic acid can be broken up into hydrogen ion and bicarbonate. Hydrogen ion is an acid and bicarbonate is a base. So wouldn't it be helpful if our kidneys could just respond to a pH problem by urinating out the thing we already have too much of and keeping the thing that we need to balance out the problem in the bloodstream? Well, that's exactly what they do. When the pH drops and therefore is more acidic, then our kidneys reabsorb bicarbonate so that bicarbonate stays in the bloodstream, and the kidneys then excrete hydrogen ion in the urine. And then in response to a more alkaline blood pH, again, it's more basic, the pH is higher, the kidneys do the opposite. To balance out that alkaline pH, hydrogen ion is now retained in the bloodstream and bicarbonate is excreted. So now a normal bicarbonate level is 22 to 26. So let's say we have a respiratory problem that's causing acidosis. Maybe our patient had too much of a narcotic and their respiratory rate is really, really slow and ineffective. So CO2 slowly starts to build up in the blood and the pH becomes acidic. Our kidneys see that and say, hey, I can help. They see that our blood has too much acid, so they get rid of additional acid and they excrete hydrogen ion into the urine. And then to help counteract that acidic pH, the kidneys also reabsorb bicarbonate and bring it back into the blood to bring the pH up. Now on the other side, let's say our patient is hyperventilating and they've blown off way too much CO2, causing low CO2 levels. And as you remember, that's going to lead to a high pH. And our kidneys respond to this by saying, looks like the blood is too alkaline. I can help with that too. I'll now get rid of bases. So the kidneys excrete bicarbonate into the urine, and then they hold on to acids in the blood by reabsorbing hydrogen ions. So as you take this all in, it can be hard sometimes to remember, would breathing slowly cause a high or low pH? Or would levels that are low of bicarbonate cause a high or a low pH? And there's a lot of ways to remember and keeping these things straight, but here's just one potential method. So using the acronym PHRC, P standing for pH, H standing for bicarbonate or HCO3, R standing for respiratory rate, and C standing for CO2 or carbon dioxide, you can fill out which would cause acidity and which would cause alkalosis or a base. So here you can see for acid, a low pH is acidic, a low bicarbonate level is labeled as acidic, a low or ineffective respiratory rate leads to acidosis, and a high CO2 leads to acidosis. And then for the base, a high pH is alkaline or basic, a lot of bicarbonate is labeled as basic, fast and deep or hyper-effective respiratory rates lower CO2 and cause alkalosis, and a low CO2 causes alkalosis as well. So with PHRC, if we do acid first, it's down, 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 up, and for base, it's up, 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 down. You may have also heard of ROME as well, respiratory opposite metabolic equal. So with respiratory opposite, you can see not only is the respiratory rate and CO2 opposite of each other, but CO2 is opposite of the pH. So when CO2 is high, pH is low, and vice versa. So this is just a quick way to remember when each value is high or low based on being acidotic versus basic. And you'll see that the CO2 goes in the opposite direction from all the others as well. So everything else is low when CO2 is high and vice versa. So hope this helps.